We'll start the recording. So last time we introduced, so in the very first class, we introduced ourselves with graphs. Say we had a 4-vertex graph, or sorry, a graph with 1 vertex and valency 8. We talked about its possible contractions like this and its symmetry factors. We also had graphs with, say, 2 vertex and multiple vertices like this, and so on. We talked about graphs with, say, graphs that have 3 hands. Here there is 4 hands. By hands I mean the valency. And we talked about graphs that has 3 hands, 4 hands, multiple hands. And we saw that the ways of contracting them is for n minus 1 double factorial ways you can contract them. And you have different types of graphs, for example, figure eights, that is like this. And this is one of them. This is one of them. And you have graphs like this for 2 vertices and valency 4. You had these 3 kinds of graphs. We talked about self-connection and connecting with the other members of the other vertex. And let's see, what else did we talk about? We talked about the symmetry factor. For example, if you have this graph, what is its symmetry factor? You can flip like this, up and down, flip the petals. So, and you have 4 petals, so 2 to the power 4. And you can place these individual petals in any order, so 4 factorial. So the symmetry factor is something like this. So symmetry factor is basically the operations you can perform on the graph and leave it invariant. And let's see, what else did we study? And we had, so I defined a function like this, which is sort of like a graph function, which generates all my graphs. For example, we had a function like this, graphs of valency 4 and n vertices. We can have different valencies, and we were dealing with graphs of valency 4. They are weighted by this factor, which is the symmetry factor, and the power of G tells me what vertex I'm looking at. For example, you can have vertex 1, which is basically this. G2, for example, G2 is G square term means you have 2 vertices, which are like something like this, and so on. So you can expand this and have G, the symmetry factor corresponding to this is 1/8, and G squared, you have this. This, and so on. So what I claimed is you can generate all these graphs from just connected ones, which is these are connected ones, that is connected with other vertex. These are disconnected ones. So I can generate all my connected ones, all of my graphs just from connected ones. This F function, free energy, sometimes it's called the free energy, or I can call my connected graph generating function or something like that. So I can get all of them from just connected ones, and it looks something like this. Minus F. Minus is just for convention. G/8. so on. So I claimed it, and we saw it to the second order that it holds, and I asked you to check for third order. So if you check, you can see. And what we saw was this partition function, that is this function of graphs. You can generate these graphs by a single variable partition function, that is something like this. If you have any questions, you can ask me. I'm just repeating the previous stuff so that you can have an introduction again. So using this, someone came and I just, okay. Yeah, okay. So using this function, I can generate my graphs. We saw that I can generate graphs of valency 4 using this partition function. Here n is the normalizing factor, and we found out to be this to be square root of 2 pi. So using this, we can generate all my graphs of valency 4. So this 1 degree of freedom partition function generates all these. And we claimed that, yeah, we claimed that these two partition functions are the same. That is this one. Am I using the same notation? Okay. One of them is, let's say this, and another is, let's say, curly z. So this is a 1 degree of freedom or one variable partition function, which is this one. And my counting graph partition function, they're the same. That is, I can generate my graphs using this 1 degree of freedom or one variable partition function. We checked it at the 0th order. It's true. And we saw it for higher orders that you can, yeah, you can generate that this duality holds. So we learned about correlation functions or expectation values, which are like this, which look like this, xk. That is, if you expand this g, you will have different powers of x coming down. If you expand this exponential, if you notice there is it's exponential, you can expand this and you'll have different powers of g coming down, and these count the vertex. As you know, the powers of g count the vertex. So all these things, and we saw that generates the required symmetry factors, that is 2n-1 double factorial, which was for distinguishable case, we had k-1 double factorial distinguishable. To do the indistinguishable part, you just need to divide by 4 factor. Since we are dealing with valency 4, you need to divide by 4 factorial per vertex. So if we take all that into account, our full expression looks something like this. Double factorial. So our full expression looks something like this. It generates all my required symmetry factors of the graph. So the sum is, remember, the sum is over vertices, not the valencies. So you're summing over vertex, and the powers of g tell you what vertex you're looking at. And then we talked about the source getting these functions, these correlation functions or expectation values, using a source term. That is, if you normalize like this, you can use the source term to bring powers of x down and then set the source to 0. That's how we did it. That is, we use the source let's give an index alpha. We use the source and set j equals 0. You can generate all these things. And since you have done Gaussian integrals, you know what the value of this integral is. So you just, let me write it for you. It's j squared over 2 alpha. So you know this. And by this, you can generate all your correlation functions or all powers of x. Okay, let's see, what else did we study? So if I, for example, if I expand this integral to remind you what it looked like, gx4 over 4 factorial. If I expand this, it looks like something like this, x4, 4 factorial, and g squared, and so on. And x4 is just so you can expand the integrals like this for if you have different, for example, so one of you asked if we want to generate, let's say here we had valency 4. If you want a if you want to describe a graph with valency 3, you need to have x cubed here. And yeah, I showed it that you can have I showed the case for x cubed graphs. And then we looked at cube graphs have this three hands coming out of them. So for the multidimensional case, my Gaussian integral, or my integral with source term, looked something like this. That's what we started last class. X transpose AX plus J transpose X. And as you have calculated Gaussian integrals in detail, you know what the result of this is. And by 0, I mean you don't have the source term. You said that j equals 0. So it's something like this, J transpose A inverse J over 2. So you can do this. Okay, let's see, what else did we study? We talked about the expectation values of, say, if we had something like this, 2n, in the same way, in a way similar to the one variable case. Where's the source term? Yes, you have to take derivatives with respect to j. I1, and you get your or this thing. Basically, you get your correlation function or expectation value, whatever you want to call them. So what happens when you, let's repeat what happens when you're dealing with such scenarios. So if you take the derivative, let's expand it out. Okay. So let's say you have some, I2 or j I3 dot 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 j I2n, and you will have these inverses corresponding to them, I1, I2, and dot 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 up to say A inverse K2n minus 1, K2n. We'll just for now accept these things. I will show you an explicit example and you'll understand better how this happens. So the only way, remember we're setting j to 0. The only way my terms survive is if I get rid of all j's by taking derivatives. That is, if all my j's are killed by the derivatives and we are left with a inverses, in only that way only that part of the function survives. So we talked about this, that if you have, let's say, if you're trying to do this xi xk, that is ji1, so ji, and set j equal to 0, you get this, which basically says the probability. So if you're looking for a physical interpretation of A inverse ik, it's just the propagation from I to k. It's just telling you that I connects to k. That's it. It's a connection, and it's sometimes called the propagator. So if you have a bunch of xi's,
is it the same propagator as the one we learn in what's the word for it again? Some integral. I forgot the name of it, but let me get back.
Are you talking about in quantum field theory?
Yeah, the one we see over there. Some F related, some.
I am pretty sure that you can get to that formulation from the matrix model, so I think maybe there's some relation.
Yeah, this is the same thing.
Okay.
This is the same thing. But we aren't dealing with that. But you'll see an example. I'll show you a very explicit example, and then you'll understand how these things work.
Okay.
So for now, just try to understand what's happening here. It's just taking derivatives, getting rid of j's, and you're left with A inverse. Okay. So this any correlation So any correlation function like this, you'll have a bunch of A inverses. You'll have a bunch of A inverses because anything other than that, you set it to 0. You set the j's to 0. Any term containing j, that is, if any of the j's remain, that term gets cancelled out because you're setting j to 0. So there's this theorem called the Wick's theorem. I'll just write it out first. Remember, it has to be k has to be equal to 2n. If we have odd pairings, they're 0. So pairs, it's the sum of pairs, and you have a product like this. I'll just give you a specific example in a bit. J A K A. That is, this comes from, okay, as you know, this is it my internet or okay. This is just, let me show you an example. What this theorem says. You can even explicitly check it by taking derivatives like that. So example, Let me show you an example. Let's see. So Wick's theorem says, so basically what Wick's theorem says is you'll have a bunch of A inverses. That is, we understood it from here. You'll have a bunch of A inverses because if there is any J term, you set it to 0 and it vanishes. Okay, so what Wick's theorem says is basically you'll have, if you're doing a correlation function or if you're calculating the expectation values like this, you'll have a bunch of A inverses. So if you see an example, let me show you an example. Okay, you'll have you can fix the ordering problem. No, wait, okay, forget about the ordering problem. Say you'll have xi, xj, because it's A inverse ij. You'll have xk, xl. You can write it as pairs. If you're confused what is happening here, just use this formula, use this relationship, and check whatever we are doing. Just take these derivatives and you will see we are left with a bunch of A's and they pair up like this. And if you want a cartoon diagram or a physical picture of what's happening, A inverse ij, as I told you, it's just I connecting to J. And A inverse KL is just K connecting to L. You can have X I connect to K, and you can have J connect to L. And you'll have another term, I connect L and J connect K. Okay.
So this is like all the ways you can connect the graph vertices together, right?
Yes. You'll understand what I'm doing when I show you the example. But for now, this is just graphs. What you said, graphs connecting with, yeah, points connecting with one another. I connecting to J, and yeah. So how many terms do we have? 3 factorial terms. That is 3 terms, which is, so if we have 2n terms here, if we had 2n terms, we would have 2n minus 1 double factorial terms. So Wick's theorem says xi k pairs so it's basically a sum over 2n minus 1 double factorial terms. That is, you'll have 2n minus 1 double factorial terms like this. For example, if you have 4 of them, that is, you'll have 3 double factorial terms. That is 3 terms. 1, 2, 3. So it's a sum over 2n minus 1 double factorial terms. And we call these things Wick contraction. If you want, for example, yeah, we call these A inverses propagators. So xi and xj, since the connection of this is sometimes called Wick contraction. That's, the naming isn't important, but yeah. So let's try to understand. So this might seem a bit confusing. Let's try to understand it for n equal to 1 scenario. That is, we don't have matrices. We just have single variables. So let's see. So what does x2n mean? We just have 2n of these x's. That is x connecting to x and so on. We have 2n of these. So if we have, let's say, x, 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 this is just xx, xx, and so on. They're basically the same, so you have to divide by some number because of fixing the repetition issue. But yeah. Okay, so, and right, yeah. So if you see explicitly, if you set the weight of this to 1, that is xx is 1, you'll see that you get 3, which is, and if you have 2n minus 1 of these, so you'll have 2n minus 1 double factorial. You can easily check for n equal to 1 scenario that you get a 2n minus 1 double factorial. That is, so the Wick's theorem is a sum over 2n minus 1 double factorial terms. 1, 2, 3. So that's what we got. So all this time we were dealing with, say, graphs with the same valency. For example, all this time we were dealing with graphs of valency. For example, if we were dealing with valency 4, we were just dealing with valency 4. We weren't dealing with valency 3 graphs and all those, but we discussed a bit in the question answer session, but we weren't explicitly dealing with them. But if you want to generate a graph of, say, all valencies, you can write a partition function like this, and we'll see an example of that. You can write a partition function like this, and this will generate graphs. So if we will have a symmetry factor like this. Graphs with nk vertices. You'll see what this means. So let's see a specific example. Let's say, I have a blue vertex that has 3 hands and a red vertex that also has 3 hands. And let's say yellow is the one connecting. Okay, so what I say is only red and blue can connect, not red with itself. That is, blue can connect with red, but red cannot connect with itself. This is not allowed, or this is not allowed. So only blue ones connect with red, and yeah, that is the only rule. So let's make a combinatorics problem like this. We can have multiple vertices. For example, we can have multiple yeah. Okay, I'm messing up the color thing. and so on. So we let's make a problem like this, that is blue can connect to, say, red. Blue cannot, blue or red cannot connect to itself. So this is a combinatorics problem. I want to have a function. I'm dealing with a problem that says that my blue vertices can connect with my red vertices, and so on. So only possible contraction is red going to blue. So first thing is we need as many reds as blue. That is, if we have one more red vertex here, it will be left uncontracted, and yeah, that will be 0. So we need as many reds as blue. Okay. So there are blue vertices which only connect to red vertices. This is our problem. Previously, we dealt with vertices which were identical. That is, if we had two vertices, there was no way of distinguishing them. They were the same. If we have a vertex like with 3 hands, they were the same. You couldn't, like, for example, distinguish them. But now we are distinguishing them by announcing that some of them are red, some of them are blue. So our coupling or our G's will look something like this: red and blue. And as a reminder to you, for a one variable case, our function was like this: x cubed, we had a G, 3 factorial. This function generated all my cubic vertices. So now I want to write an integral like this that solves this problem of combinatorics. That is, this solves the red connecting only to blue and red not connecting to itself, this problem. I need an integral like this which solves this problem. Previously, our integrals were indistinguishable. That is, our vertices were not integrals. Our vertices were indistinguishable. I couldn't distinguish between them. That is, if I had two vertex, there's no way of saying that this is different from this. But now I'm saying that one of them is red, one of them is blue. And I'm announcing that red can only connect to blue, but it cannot connect to itself. That is, yeah. So any ideas how we can solve this problem?
Well, it wouldn't be very fair for me to answer because I've already watched the lecture, so I'll let someone else answer.
Okay, let's say does anyone want to answer how we can make the connections? Even if you watch the videos, it's fine. So tell me how we can connect them.
So the way you would do it is it would be a two-dimensional integral.
Why?
And you would, because you have two different kinds of vertices, they have to be encoded by two different variables.
Exactly. So.
And you need a matrix which represents your propagator. And you want to put the coefficients in it such that they represent the weight of the connections.
Okay, so let's stick to what you first said. We need a two-dimensional integral, right? So, okay, so let's say dx dy. So what will be in my exponential term?
The first one will be the kinetic term, minus x squared over 2. Then you'll have then you have a matrix term. You have the x. Oh, right. I think it'll be minus xy
Yes.
over 2, or maybe there's no 2. I forget. And then you have x in g red into, yeah, okay. So, and
Yeah.
then you need a similar one for the blue with a y cube over 3 factorial.
Okay. Yes. So this function, this partition function will solve the combinatorics problem. So this is a claim. So how do I say this solves the problem? Okay. So this is basically, you have two variables. You can see this as an n equal to two-dimensional, let's write multi-dimensional Gaussian integral. So a way to write it is, you can write it as vectors. That is, you can write it, you can write, for example, you can write x as, let's say, x1, x2, and the transpose of it will be x1, x2. So if you remember, so we can write it like this, and it's just here x1 is just x. Let's make it x1 and avoid the confusion. x2 and x1, x2. Okay. So if we write it down, it's just x1, x2, a11, a12. These are matrix elements. I'm writing the terms out explicitly. 2, 2. So okay. So A, to get this thing, can someone say how I need to fix my A's? Do we have a square term? No. So A's should, this is my A matrix. A should be 0. This should be 1, 1, 0. That is, if you multiply it out, you will get x1, x2 minus half x1, x2 minus half x1, x2. Other terms are 0 because, yeah, that's how we give it a matrix interpretation. Just if you're confused about how this holds, just check it. It's just, yeah, the matrices have to be like this, otherwise you won't get minus x1, x2. So the matrix is like this, and some of those of you who know that this matrix, this is the sigma matrix. Those of you don't, it's fine. A is a matrix, is a sigma matrix or poly matrices. So A, the inverse of A is just A itself. You can check. You can multiply. Yeah, you can multiply A 2 times and see you will get identity. So the inverse of A is itself. Yeah. So this is something like this. So now what happens to to my correlation functions? That is, what happens to xx? Say this is x1, x1. This is A inverse 1, 1. What is A inverse 1, 1? 0. x1, x2. What is A inverse 1, 2? It's just 1. And what else have we got? x2, x2. This is A inverse 2, 2. This is 0.
Yeah, I was thinking about it like this, but I was jumping the gun and thinking about this way of thinking of it.
Yeah. So if you know, okay, so this explains that X1 can only connect, or the reds can only connect to the blues, but reds cannot connect to red itself. Can you explain, Saif, how this holds?
Well, X1 connects to, X1 represents red and X2 represents blue. So the expectation of that represents their connection.
Yes.
So the fact that the connection weight is 0 means they don't connect. And then the fact that X1, X2 gives 1 means they do connect.
Exactly. So one way of seeing this is, if you're confused how this holds, I would encourage you to expand this integral. If you expand this integral, you'll see that, okay, let me expand it. But as Saif said, if you have this red, and say this is red as well, the propagator between them is 0. Which one you pick, you might pick X1 to be red, X2 to be blue. You can do whichever you want, but X1 connecting to X1, it's 0. It's weighted by 0. And blue, again, blue, 0. But red connecting to blue, X1, X2, it's 1. So if we expand this Z, this red-blue partition function, if we expand this out, the first term is 1. The second term is G red, G blue. And you have 1 over 3 factorials coming out. If you're confused, what is this? G red, it's X1 cube over 3 factorial. If you remember how we expanded it, 2x2 cube, there's no space, x2 cube 3 factorial. Where did I expand them? Yeah, that's how we expand. Yeah, the powers of G. So if we expand it out, we'll have these things. So if you write it out like this, x1, 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 x2, 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 because you have x cubed, right? X1 cube and x2 cube, you can write it out like this. And remember, now you have to use the Wick's theorem. That is, x1 connecting to x1, you know it already, that's 0. And x2 connecting to x2, you know that's already, that's 0. So only term surviving here will just be the terms which are x1, x2. Only these terms will survive. That is x1 connecting to x2. So how many of these terms do you have? Right. There's other terms. How many of these terms you have? If you expand it out like this, you'll have x1, x2. So if you use Wick's theorem, and if you know what it, yeah, if you use Wick's theorem, you'll see you'll have, or you can, or forget Wick's theorem.
I think it should be 3 factorial.
Yeah, it's
right.
3 factorial. Yeah, but you can use Wick's theorem, but if you don't want to use it, one of the way of doing it is just think of how many x2s x1 can connect to.
Yeah, that's the way I did it.
Yeah, so x1 can connect to any of the three of these things. So 3. The first x1 has 3 options. The second x1 has 2 options. The third one is left with 1 option. So it's just 3 factorial. And G red, G blue. This is just 1 over 3 factorial. plus you'll have higher order terms, that is G squared red, G squared blue terms, and you can generate all these things. So
Oh, by the way, you can't have a G square red with a G blue because you have to have the same number of red and blue, right? Is that the right way to think about it?
you can have G squared red and G squared blue.
Oh, but I mean, you can't have different numbers of the two because then there wouldn't be
Yeah.
enough connections. Yeah.
Yeah. For example, if we have, let's say, this is a red one, this is, let's say, red, this is blue. You can have these terms because if you're expanding it, you'll have different powers. So you will have these terms, obviously, but they're zero because, yeah, this thing can connect to this, but this guy is left alone. So that will be zero. So the best way to understand these things is expanding out, doing it yourself. Try to do it yourself. Try to expand these things. If you're stuck, just ask me how to proceed. So what is this graph? What graph does this correspond to? That is, you have two vertices, say red, blue, and they connect like this. So what is the symmetry factor associated to this? It's 3 factorial.
Because of the 3 factorial ways of permuting the lines.
Exactly, 3 factorial ways of permuting the lines. So the symmetry factor of this is 1/3 factorial. So previously, if you remember, when we couldn't distinguish them, what was the scenario again? Can you tell me, Saif, what would happen if we couldn't distinguish them? Here we can distinguish them by saying some of them are red, some of them are blue.
Oh, then you could flip the 2 vertices and get another 2 multiplied in the bottom. Yeah.
Right? Yeah, because it wouldn't change the symmetry, right? So you can have this one and the same. Yeah, you have an option to flip it. Like you can flip the vertices. This can be here or this can be here. It doesn't matter. So you can flip the vertices. That's why you have a symmetry factor of 2. Okay, so in this red-blue example, we tried to construct a graph with, so we had 2 different kinds of vertices, which we labeled blue and red, and blue can only connect to red. We placed this condition, and even for that problem, what we have is two-dimensional. Where is that? Yeah, two-dimensional Gaussian integral, or two-dimensional partition function, and by that two-dimensional partition function, I can solve this combinatorics problem associated with these graphs. You can solve it to any orders of G, that is any number of vertices you have, you can solve this. So one way of solving this is, say, if you know the A inverses, that is, if you know how these connects, for example, before we even started, I told you that red can connect to blue. That is, if you think about our A inverse matrix, so let's say 1, 1 should be 0, because we knew beforehand red cannot connect to red, and 2, 2 should be 0. The only non-zero components of this would be 1, 2, and 2, 1, right? So if we knew the inverses, if you think about solving this problem, since you know the inverse matrix, that is, if you know how these connect, you can use this inverse matrix and find its inverse, and you can ultimately find the red-blue partition function. Say we had a different problem. We had, say, 3 kinds of vertices. That is red, blue, and green. If you knew how these two connect, you can find the inverse matrix, and the inverse of that matrix, you can get the A, and you can write your partition function. That is, you can write this out. That is, you can backtrack if you know what's happening. If you know that how graphs connect, you can backtrack and get your partition function. For example, if we have, let's say, a quartic vertex, for example, let's say example 2. Let's label them A, B, C. If you have quartic vertices, that is, if you have a sum over such graphs, quartic as in this has 4 hands, if it's difficult to understand. So just look, it's a very badly drawn graph. But yeah, each of them have 4 hands. Each of these vertices, A, for example, A, it has 4 hands. So you can construct graphs like this. Let's say we place the condition that A can only connect to B and C, not A cannot connect to itself. If you place such conditions, can you tell me what the inverse matrix would look like? It will be a 3-dimensional integral. Obviously, you have 3 kinds of vertices. So can somebody tell me what the inverse matrix would look like?
All the diagonal elements 0.
And the rest of them would be 1.
Yeah, very good. So if you know how these things connect, that's it. So yeah, so A connects to BC. You can have different variables. You can assign them different variables, let's say X, Y, and Z, and you can construct your Gaussian integral like this. Remember, this will have, yeah, this is a, yeah, if you want me to write it down, this will have minus half XYZ plus A X4 factorial. The factor would be 2 pi, I think 3 by 2 or something. Yeah, I think it should be 3 by 2. Okay. 4 factorial. And this solves our problem. It is an exponential and so on. So this solves our quartic vertex problem. So any kinds of, so the lesson from this is, any kind of vertex we have, we can solve them using either a single variable Gaussian integral or partition function, or a multivariable one. We just need to understand the problem. We can find the A inverse and then backtrack and then find the other stuff. So this is one way of solving combinatorics problem related to any graphs of, let's say, any vertices you have. If you want to distinguish the vertices, you can also solve that. If you don't want to distinguish the vertices, you can solve that. So in any way you want, you can solve these problems. You just have to understand the problem. And if you understand the problem, the best way is to look for the A inverse. If you know the A inverse, you can backtrack and find your partition function. And if you know your partition function, you're done. You can generate all the symmetry factors, anything you want associated to the graph. So let me give you a bit of analysis in what happens in say a physics problem. A physicist would approach this. For example, To a physicist, these points, let's say A, B, and C, they would have, think about this. In your room, how many points do you have? You have infinite number of them. I mean, yeah, because you can count. So you can define different points in your room. Let's say one centimeter difference between each point is 1 centimeter. You'll have a lot of points in your room. So you can associate, you can draw graphs, basically graphs in your room, and use a partition function to explain different points, graphs forming in your room. That is, for example, let's say you have different points P1, and you have a lot of points in your room. Let's say you have another point P2. You can connect them. You can form graphs in your room and explain using this multidimensional Gaussian integral about how different graphs might look like. Yeah. So what physicists do is they have infinite number of them. They consider them as fields, and each point they have different so in space you have infinite number of points, and different points connecting them, they're called propagators. So this P1 and P2, it's just A inverse P1, P2. It's just the propagator connecting these 2 points. So this is what physicists do in quantum field theory. So they describe the propagation of this point to here. So this is what a physics picture would look like. These are basically particles in space. So you can have a physics analysis of this whole problem, but we are not going there. We are just dealing with the, we are just basically dealing with graphs. We don't want to understand the physics, how a physics picture might look like. Okay. So this is all about graphs. So our graph analysis almost ends here. And by now we know how to generate different kinds of graphs with different vertices, with different, let's say with different kinds of vertices, with different valency, with different, if we can even color code them, we can even identify them, we can do a lot of things with graphs. And if we know, yeah, if we can construct the partition function, we can calculate different symmetries they have. We can do all sorts of things with our graphs if we just find the partition function. So the basic problem boils down to just finding the partition function and doing the problem. And your problem is almost solved. You just need to calculate the corresponding factor. You can look at the graph and calculate its symmetries. You can calculate the correlation functions. You can even find what different symmetries they would generate and so on. So this is where our graph discussion ends. And now, as I told you, we'll go from something called graphs to maps. So a graph would, for example, our graph was something like this. You can have different kinds of graphs on a surface. And so on. Yeah, this is a graph. So what is a map? A map is the same thing as a graph, but only thing that isn't allowed is this, overlapping. That is, I crossed over. Crossing over isn't allowed in a map. This is not allowed in a map. So the maps are the same thing. I'll define it in a bit for your understanding. So this overlapping thing is not allowed in a maps. And sometimes these maps are called planar graphs because they are drawn on a plane. So these can be drawn on a plane or a sphere. And yeah. So why do we need the notion of maps? That is our first question. Since we were doing completely fine with graphs, remember what we initially started with. We started with a random surface, a two-dimensional surface. And we said we want to discretize this because we want to describe the surface. Our initial intention was this, a 2D surface. And anything, you can break it down. You can discretize this, right? For example, you can look at even you can look at your pencil. It's just made of atoms, so everything can be discretized in that sense. So we want to discretize this and describe the surface. That was our initial idea behind starting this whole discussion. But one problem we face in case of graphs is, for example, graphs, they don't have a notion of what is near and what is far. And what do I mean by that? For example, they don't have a notion of
Distance from one point to another.
yeah, yes, that's a nice way to say it. So for example, if you have a graph, let's say they're indistinguishable. You have a graph like this. This point, let's make another point. For example, this point, I can say this is far from this point. But if I connect them, it's not very far. That is, you can go directly from there. And I can make this point come here. That is, I can reconstruct the graph because they are indistinguishable. So the notion of distance fails. And since I can jump over in a graph, for example, I can do these things. Yeah, this thing. I can do these things. These are a problem. Why? Because in 2 dimensions, if you're jumping over, you move to another dimension. Think about this. Just hold your breath. Think about your table or anything that is 2-dimensional. If you are jumping over any surface, or the overlapping takes you to another dimension, right? That is, you're moving to 3D. If you're in 2D, overlapping lines take you to another dimension. That is, you have to jump over. For example, if you have this, so I want to go there. So I have to basically jump over this. So that's not a good way of doing things in 2 dimensions. So that's why for these 2 reasons, graphs are not a good idea for doing, let's say, for describing a 2D surface or so on. So this is just the motivation. In random matrix theory, we all will be dealing with our maps. So they come from matrices. We will see I think we'll see that tomorrow, and more of this when we are doing our formal introductions to random matrix theory, formal stuff in random matrix theory. But the basic idea is this. So the basic intuition behind this is this. One, graphs do not necessarily offer the notion of near and far, but maps, they offer that, because since this is not allowed, this point is actually far from it. This point is actually far from that. So they offer the notion of distance. And second, they keep things in 2 dimensions. For example, if you want to describe things in 2 dimensions, map is a better candidate than graphs. So this is one of the ideas. And so to describe a 2-dimensional surface, we need a sum over maps, not graphs. So graphs, not a good idea. This is the motivation for studying maps. So what are maps? Or in more formal language, they're called planar graphs. So what are maps? These are graphs that we draw on a surface without, say, lifting the pen or intersecting the other line. And another criteria is whose faces are okay. How many of you haven't heard this word? Or you haven't ever come across this?
I sure did. Went through this. Okay.
Can you tell me?
I did not.
Okay. Can someone tell me what, if those of you who know this, I'm pretty sure some of you know this. Can someone tell me what isomorphism is, or isomorphic is?
Being the same shape or form or something.
Yes, they're being the same. For example, when you say plane, a plane, as in a plane is isomorphic to a sphere. Can someone say what this means?
I mean, there's a bijective map between them. So
Yeah.
you can smoothly deform the plane into a sphere if you consider that there's one point at infinity that produces the vertex of the sphere.
Yeah, it's like the complex half Riemann sphere or something that maps the whole plane on a sphere and the top of the
Yeah,
sphere.
like the stereographic projection. Yeah.
Exactly.
Yes.
Very good. Very good. Very good. Yes. It's the same. That's like you are bending the plane and you're making it you're making it closed. You're basically, if you think of the plane having hands, you're closing the hands to make it a circular shape. You can do that. So isomorphism is basically, for example, when we say isomorphic, it's if you want a more formal language, it's basically a bijection. That is, if you define a map, you can go from one of these to the other, and you can go one of these to the other. But in a more physics language, or in a more intuitive language, so a plane is the same as a sphere, or let's say as a cube. By that I mean you can deform the shape and turn it into, let's say, you can deform the plane and turn it into a sphere or a cube. And for those of you who have heard the mathematics joke that a mathematician cannot, for example, cannot distinguish between a mug and a donut, have you heard of it?
Yeah, it's the classic topology joke.
Yes, sir.
So it's because what do you call this? A mug is a genus 1 surface. What is a genus 1? Genus 1 means basically holes. For example, sphere, planes, these are all genus 0 surface. Genus is basically a number that we assigned to surface. Genus is basically a number that we assign to surfaces. So what you need to understand is, so a mug has genus 1. Why? There's one hole, right? A donut also has a one hole. So if you can deform a mug or a donut into one another. If you we don't know for sure. Tasso asked, why is the universe a genus 1 surface? We don't know that for sure if it's a genus 1 surface. We don't know what the genus of the universe is. And for example, that is one problem of this genus thing. Those of you who have done topology, you might know this, that this genus or genus thing is very special in 2 dimensions. In higher dimensions, the idea of these things become very shaky, and we don't have, I believe we don't have topological invariance, what you call that, Euler characteristics in higher dimensions.
I think the issue is that in 2D, you can classify all topologies by their genus. But in higher dimensions, we have no full set of parameters to completely classify all topologies. Definitely not just by their genus.
Exactly. That's one of the problems in higher dimensions, but unfortunately our universe is a 4-dimensional. It might be of higher dimensions if you are string theorist, but
Depending on who you ask, yeah.
if you ask me, I believe it's in. It's if you ask me, I'll surely say it's not a 4-dimensional universe. But okay, so going back to our example, so a mug is isomorphic to a donut. So that is, a mug can be deformed and made into a donut. If you're confused about how to do it, there are various YouTube animations of mug transforming into donuts and genus 2 surfaces transforming into other genus 2 surfaces and a plane transforming into a sphere. Just go to YouTube and search for these things. You'll have a very intuitive picture of how these two things are happening. So if you take a mug, you can deform it and make it into a donut. These are very cool stuff, so you can search it up. So deforming means you don't tear the surface, you just deform it. For example, yeah, it's good to remember it. So these are genus 1 surfaces. And you can have a genus, basically, if you're confused what a genus is basically a hole. A mug has one hole. A donut has one hole. So genus is basically a hole. And you can have different, for example, hold surfaces. For example, this is genus 5 surface. And so on. So a nice thing about 2D is, since we are dealing with 2 dimensions, so a nice thing with 2D is we can describe any surface with the genus. For example, any surface, plane, sphere, cube, anything without a hole, is a genus 0 surface, and they're all equivalent. We'll take all of them to be equivalent. If you're doing something on one, let's say the plane, if you're dancing on the plane, it's the same thing as dancing on the sphere to a mathematician. So yeah. So by isomorphism, those who haven't done topology or who have no idea of what this is, so isomorphism is basically being the same thing. That is describing, that is doing my work. It's the same if I'm doing in a mug or with a donut, because I can transform one into the other. So one suggestion for those who haven't come across genus, topology, or things like that, you just need to understand what a genus is. And I think you understand that by genus, I just mean whole. And you just go to YouTube and look for this. You'll understand what I'm talking about. Just see some animations and you'll understand. Okay. So this is the idea. So a map is a graph that we draw on a surface whose faces are isomorphic to disks. I'll just take 5 more minutes and I'll just end today's session, and we'll discuss the other stuff tomorrow. That is, what do I mean by faces? I should specify that first. For example, this is a map. So how many faces does it have? Let's say I draw it here. How many faces does it have? Can someone say?
3.
Yeah. So by faces, I mean this space I'm talking about. So this, and by isomorphic, I mean they're the same as disks. Disks are just stuff like this. So by isomorphic, I mean they're the same. You can understand why they're the same, because there's no holes. So this is a genus 0 surface and this is a genus 0 surface. And you can deform this triangle like this. You can deform this into a disk. So by isomorphic, I mean they're the same. So I can draw various kinds of graphs on, various kinds of maps on a 2-dimensional surface. For example, our figure 8 our very first graph, I can draw it on the map. I can draw it on a surface like this. But the last point that I want to make is, but I can draw this. Because this is overlapping and I have to jump over things. So this is not a map. Because you need to lift the pen to jump over. So this is not a map. And since another criteria of this is checking if this is isomorphic to disks, this is not isomorphic to disks because, yeah. So in the lectures of Pedro, he gives an intuitive picture of what faces are. He says that all of you have used paint in high school, in computers, the paint. So if you click here, if you try to color these things, if you click, let's say red, if you do it red, you can do it blue, and you can do it green. So you'll have different colors. So faces are basically the place you cover when you click a different color. It's just the place you cover in a graph. It's just yeah. So for example, in here, you'll have again 3 faces. You just colored them, and yeah, they are the faces. But here, I'll explain this more in the next class. Here, you can have faces. If you try to color them, you'll see that, yeah, because there is an overlap, they aren't isomorphic to disks. I'll describe it in the next class, but yeah, this is a good stopping point. Okay, let's see if I missed anything that I wanted to say. No, I think I've covered. Okay, let me stop the recording and I'll listen to you.